Hello there, and welcome to the Snoozing Ideas channel. I'm so glad you've found this quiet corner of the internet tonight. Perhaps you've had a day filled with busy thoughts, or maybe you're simply seeking a gentle way to drift off while learning something wonderful. Whatever brought you here, you're exactly where you need to be. Take a moment to settle in. Let your breathing find its natural rhythm, and feel the weight of the day begin to lift from your shoulders. Tonight, we'll be basking in the warm glow of the most relaxing facts about the sun to fall asleep to dreamy science. Our nearest star has been watching over Earth for billions of years, a constant presence in our skies, even when hidden behind clouds or the horizon. There's something deeply comforting about its ancient rhythms and golden light, isn't there? Let's begin. The sun holds almost everything in our solar system within its gentle grasp. It contains 99.86% of all the mass in our solar system, creating the gravitational anchor that keeps planets, asteroids, and comets in their cosmic dance. Scientists have measured this mass through careful observation of orbital mechanics and the mathematical principles that govern celestial bodies. The sun's immense gravity shapes the very fabric of space around it, bending light and warping time in ways we're still coming to understand. Could anything else in our cosmic neighborhood ever compare to such magnitude? Like a parent cradling children in steady arms, our star holds its family of worlds in a balance so perfect we rarely notice its constant embrace. Sunlight embarks on an extraordinary journey before touching your skin. It takes approximately 8 minutes and 20 seconds for light to travel the 93 million miles from the sun's surface to Earth. This consistent delay means the sunlight warming your face was created before you began reading this sentence. Scientists calculate this travel time using the speed of light, 186 to 282 miles per second, and the average distance between our planet and star. By the time we see the sun, we're actually observing its past state. The light arriving now carries information about what happened minutes ago. A small but poignant reminder of how we experience time across the vastness of space. The heart of our sun burns with unimaginable intensity. Deep within its core, temperatures reach about 27 million degrees Fahrenheit, creating conditions where nuclear fusion continuously converts hydrogen into helium. This extreme heat overcomes the natural repulsion between atomic nuclei, allowing them to merge and release energy. The pressure at the core is so immense that atoms are packed tightly together, increasing the chances of fusion occurring. Though we cannot directly observe this furnace, its energy signature tells us exactly what's happening. Like a cosmic hearth that never extinguishes, this stellar forge has burned for billions of years, providing the steady warmth upon which all earthly life depends. Every moment, our sun performs an alchemical transformation on a cosmic scale. Each second, it converts roughly 600 million tons of hydrogen into 596 million tons of helium, with the remaining 4 million tons becoming pure energy. This mass-to-energy conversion follows Einstein's famous equation ENmc2, demonstrating how a small amount of matter yields tremendous power. The process has continued uninterrupted for billions of years, fueling all life on Earth. What other wonders might emerge from such persistent transformation? The sun's quiet sacrifice and matter becoming light creates the constant radiance we often take for granted, a stellar breath exhaled across our solar system. Our sun wears a deceptive appearance in the vastness of space. It is classified as a G-type main sequence star, commonly called a yellow dwarf, though it appears white when viewed from space without Earth's atmosphere. This classification comes from analyzing its spectrum, which reveals its composition and surface temperature of about 5,500 degrees Celsius. The apparent yellow color we see from Earth results from our atmosphere scattering blue wavelengths more effectively than red ones. Among the billions of stars in our galaxy, the Sun sits in the middle range, neither particularly large nor small. Its unassuming nature belies its perfect suitability for life, a modest star creating the exact conditions needed for our existence. The Sun offers Earth an abundance of energy beyond our current capacity to harness. Solar energy reaching our planet in just 1 hour could theoretically power all human civilization for an entire year if we could fully capture and store it. This tremendous energy flux amounts to approximately 173,000 terawatts, striking Earth continuously. Scientists calculate this by measuring the solar constant, the intensity of sunlight per square meter, and multiplying it by Earth's cross-sectional area. Imagine what might be possible if we could perfect our solar collection technology. Like an eternal wellspring flowing freely through space, the Sun's energy bathes our world in potential, waiting for us to develop the wisdom to receive its gift. The Sun dances to its own rhythm, turning at different speeds across its glowing face. It rotates on its axis approximately once every 25 days at its equator, but takes about 35 days to complete a rotation at its poles. This differential rotation occurs because the Sun isn't solid, but a massive ball of plasma, electrically charged gas that flows and shifts. Astronomers discovered this phenomenon by tracking sunspots as they moved across the solar surface. The fluid nature of the Sun allows its equator to spin faster than its poles, creating complex patterns in its magnetic field. Like a slowly turning cosmic carousel, our star spins in silent splendor, its uneven rotation painting invisible patterns across its luminous sphere. Sometimes, the Sun releases its pent-up energy in spectacular bursts of light and matter. Magnetic field lines occasionally become twisted and snap, releasing energy equivalent to billions of atomic bombs in events called solar flares. These tremendous explosions occur when magnetic tension builds up in the Sun's atmosphere and suddenly releases, like a cosmic rubber band stretched too far. Scientists monitor these events using specialized satellites that can observe wavelengths invisible to human eyes. When particularly powerful, these eruptions can send storms of particles toward Earth. What cosmic forces could create such magnificent displays? These brilliant solar tantrums remind us that even our seemingly peaceful star harbors tremendous power beneath its glowing surface. The visible face of the Sun is surprisingly cool compared to what lies beneath. The photosphere, its apparent surface, maintains a temperature of about 10,000 degrees Fahrenheit, much cooler than its core, yet still hot enough to vaporize any earthly material instantly. This relatively cooler region is where most visible light originates, streaming outward from the solar interior. The photosphere isn't solid, but rather a layer about 300 miles thick where solar gases become transparent enough for photons to escape freely into space. Through specialized telescopes, this region appears granulated, like the surface of simmering oatmeal as convection cells rise and fall. This luminous boundary between Sun and space marks where stellar energy begins its journey outward, a threshold between worlds. Arcs of fiery plasma dance above the Sun, in graceful suspended bridges. Prominences are loops of glowing material that can extend hundreds of thousands of miles above the Sun's surface, following magnetic field lines like cosmic sculptures. These structures contain material at temperatures of thousands of degrees, suspended against gravity by powerful magnetic forces. Some prominences remain stable for weeks or months, while others erupt dramatically into space. When viewed during solar eclipses, they appear as brilliant red curves extending from the darkened disk. Like rivers of fire flowing through invisible channels, these magnificent arches remind us that the Sun is not just a ball of gas, but a complex system of interacting forces and flowing energy. Our Sun gradually becomes lighter as it shines. It loses approximately 4 billion kilograms of mass every second through the conversion of matter to energy in nuclear fusion. This seemingly large amount represents only a tiny fraction of the Sun's total mass of 2 × 10⁻³ kilograms. At this rate, the Sun has lost only about 0.05% of its original mass over its 4.6 billion year lifetime. The energy released from this mass conversion travels outward from the core, eventually reaching Earth as light and heat. The steady diminishment continues with perfect constancy, a cosmic timekeeper marking the passing ages. Like a candle slowly burning, our star consumes itself to illuminate our world, a sacrifice measured in the steady subtraction of its substance. Dark islands drift across the Sun's bright face in slow migration. Sunspots appear dark because they're about 2,700 degrees Fahrenheit, cooler than the surrounding photosphere, though still blazingly hot at about 7,300 degrees. These cooler areas form when concentrated magnetic fields inhibit the normal convection that brings heat to the surface. Scientists have observed and recorded sunspot patterns since Galileo's time, noting their 11-year cycle of abundance and scarcity. Some sunspots grow large enough to swallow Earth several times over, while others remain relatively small. Though they appear as blemishes on our perfect star, these temporary markings reveal the complex magnetic personality of the Sun, like cosmic freckles telling tales of stellar weather. The Sun harbors a perplexing mystery in its outer atmosphere. Its corona, the outermost layer visible during solar eclipses, mysteriously reaches temperatures of over 2 million degrees Fahrenheit, despite being farther from the core than the cooler surface. This temperature inversion defies simple thermodynamic expectations, as heat typically decreases with distance from a source. Scientists propose several explanations, including magnetic reconnection and wave heating, but no single theory fully accounts for this phenomenon. The corona extends millions of miles into space, so rarefied it would be considered a vacuum on Earth. Like an ethereal crown adorning our star, this shimmering atmosphere challenges our understanding, a whispered reminder that even our closest cosmic companion holds secrets we've yet to fully unravel. A constant stream of particles flows from the Sun into the deepest reaches of our solar system. Solar wind consists of charged particles streaming from the Sun's corona at speeds of 250 to 750 kilometers per second. This invisible river of plasma carries pieces of our star throughout the solar system, taking about 4 days to reach Earth. The solar wind shapes the tails of comets, pushing them away from the Sun, regardless of their direction of travel. It also creates the boundary of our solar system where it meets interstellar space, forming a bubble called the heliosphere. Might this stellar breath reach farther than we've yet discovered? Like a whispering breeze from a cosmic ocean, the solar wind touches everything within its reach, a tangible connection between our star and its planets. Our sun is itself in motion, carrying us through the vastness of space. It completes one orbit around the center of the Milky Way galaxy approximately every 225 million years, traveling at about 450,000 miles per hour. This means the solar system has circled the galactic center only about 20 times since the sun's formation 4.6 billion years ago. The sun doesn't travel alone, but moves with a collection of nearby stars called the local group. The path isn't perfectly circular, but rises and falls through the galactic plane. The last time the sun was in its current galactic position, dinosaurs had not yet evolved on Earth. Our star's stately procession continues without pause, a celestial pilgrim on an endless journey through the cosmic wilderness. Ghost-like particles stream through your body every second, messengers from the sun's core. Neutrinos produced in the sun's core can pass through the entire Earth without interacting with a single atom. About 65 billion solar neutrinos pass through every square centimeter of Earth's surface each second. These nearly massless particles travel at nearly the speed of light and are extremely difficult to detect because they rarely interact with other matter. Special underground detectors filled with thousands of tons of liquid can occasionally capture the faint signal of a neutrino collision. What might we learn if we could speak their silent language? Like cosmic phantoms, these particles connect us directly to the heart of our star, passing through us as if we were merely shadows in their path. Our sun undergoes a complete personality change every decade or so. Its magnetic field reverses polarity approximately every 11 years, marking the solar cycle from one solar maximum to the next. During this cycle, the sun's north magnetic pole becomes the south pole and vice versa. This transformation isn't merely superficial but affects the sun's behavior, changing the frequency of sunspots, flares, and coronal mass ejections. Scientists track this cycle by counting sunspots, which increase during solar maximum and decrease during solar minimum. The precise mechanism driving this cycle remains incompletely understood. The sun's rhythmic transformations continue with clockwork regularity, a cosmic heartbeat pulsing through our solar system, influencing Earth's space environment in its quiet revolution. Sometimes, the sun erupts with enough force to influence Earth's technology. Coronal mass ejections can release billions of tons of plasma into space, sometimes disrupting satellite communications on Earth. These massive eruptions can travel at speeds up to 3,000 kilometers per second, reaching our planet in as little as 15 hours. When they interact with Earth's magnetosphere, they can trigger geomagnetic storms that induce electrical currents in power grids and communication systems. The largest recorded event, the Carrington event of 1859, caused telegraph systems to catch fire and aurora displays to be visible as far south as Cuba. While our star typically nurtures life on Earth, these occasional solar storms remind us of its tremendous power. Celestial tempests capable of reaching across the void to touch our technological civilization. Our sun has a surprisingly delicate constitution for such a powerful object. Its density is about 1.4 times that of water, much less dense than rocky planets like Earth. If we could place the sun in an enormous ocean, it would float, unlike Earth, which would sink. This relatively low density occurs because the sun is composed primarily of hydrogen and helium, the lightest elements, and because its tremendous heat keeps these elements in a gaseous or plasma state. The density isn't uniform throughout the star, but increases toward the core where pressure is greatest. Despite its fluffy nature, the Sun's enormous volume gives it its tremendous mass. Like a cosmic soap bubble filled with fire, our star combines ethereal lightness with overwhelming power, a paradox burning in the center of our solar system. The Sun's surface seethes with ceaseless motion, visible only through careful observation. Granulation patterns on its surface are convection cells about 1,000 kilometers across, constantly bubbling and changing. Each granule lives for only about 8-20 minutes before dissolving and being replaced by new formations. These patterns result from hot plasma rising from below, cooling slightly at the surface, and then sinking back down in an endless cycle. Through high-resolution telescopes, the Sun's surface resembles a pot of boiling oatmeal, with brighter centers where hot material rises and darker boundaries where cooler material descends. This constant churning brings energy from the Sun's interior to its surface, where it radiates into space. The Sun's seemingly solid face is actually a shifting mosaic of rising and falling currents, a dynamic tapestry woven of light and heat. Every moment, the Sun releases more energy than humans have produced throughout all of history. It radiates energy at a rate of about 3.10^26 watts, which has remained relatively constant for billions of years. This tremendous power output equals approximately 9.5 x 1016 tons of TNT exploding every second. The Earth intercepts only about 1/2 billionth of this energy. Yet this tiny fraction drives our weather, powers photosynthesis, and sustains virtually all life. Scientists measure this output using sophisticated satellites that detect the Sun's light across various wavelengths. The stability of this radiation has provided the consistent conditions necessary for life to evolve. Like a perfectly calibrated lamp that never flickers, our star has offered its steady light through the ages, an astronomical constant upon which all terrestrial life depends. Enormous waves rush across the Sun's surface in the aftermath of cosmic explosions. Solar tsunamis can race across the Sun's surface at speeds of up to 250,000 miles per hour following solar flares. These waves of plasma stand taller than Earth itself and can travel completely around the Sun in a matter of hours. First observed by the SOHO spacecraft in 1997, these tsunamis compress and heat the plasma as they move, creating visible ripples across the solar surface. The waves help scientists study the Sun's atmosphere and magnetic field in ways otherwise impossible. The phenomenon reminds us that the seemingly steady surface of our star experiences violent cataclysms beyond anything possible on Earth. Like ripples on a pond of fire, these magnificent waves spread energy across the face of our star, cosmic echoes of tremendous power. If you could stand on the Sun, you would be instantly crushed by its tremendous gravity. The Sun's gravity is 28 times stronger than Earth's gravity at its surface, making a 150-pound person weigh over 4,000 pounds there. This powerful gravitational field keeps the planets in their orbits and helps maintain the Sun's spherical shape despite its rotation. The Sun's gravity is strong enough to bend space-time noticeably, an effect that helped confirm Einstein's theory of general relativity during a solar eclipse in 1919. Though the Sun contains nearly 100% of the solar system's mass, its gravitational effect weakens with distance according to the inverse square law. Somewhere in this delicate balance of forces, our planet found its perfect place, held in a celestial embrace, neither too tight nor too loose. A common element on Earth was first discovered in the heavens above. Helium was first discovered on the Sun through spectroscopy before it was found on Earth, giving the element its name from helios, the Greek word for sun. In 1868, astronomers analyzing the Sun's spectrum during a solar eclipse noticed a yellow spectral line that didn't match any known element. This mysterious element was later found on Earth in uranium minerals and eventually isolated as helium, the second most abundant element in the universe. Today, we know helium makes up about 24% of the Sun's mass. Helium's extraterrestrial discovery reminds us that the composition of stars and Earth are fundamentally connected. From this celestial association came its eternal name, forever linking a simple element with the blazing star that revealed its existence to curious human eyes. During rare solar eclipses, a reddish layer of the Sun briefly reveals itself to watching eyes. The chromosphere, a layer above the photosphere, appears as a thin red rim around the darkened solar disk during total eclipses due to hydrogen emissions. This layer extends for about 3,000 miles above the Sun's visible surface and maintains temperatures between 7,000 and 25,000 degrees Fahrenheit. The name chromosphere means sphere of color, referring to its reddish appearance. This region marks the transition between the relatively cool photosphere and the extremely hot corona. When not in eclipse, the chromosphere can only be observed using specialized instruments that isolate specific wavelengths of light. This hidden layer of our star appears only in moments of perfect alignment, a crimson ring emerging from behind the moon's shadow to remind us of the Sun's layered complexity. The Sun gently pulses like a living heart, though we cannot see this motion with our eyes. Solar oscillations cause its surface to move up and down by small amounts, allowing scientists to study its interior structure. These vibrations, typically less than 10 kilometers in amplitude, are caused by sound waves bouncing around inside the Sun. By measuring thousands of these oscillations with different frequencies, astronomers can map the Sun's interior in a technique called helioseismology, similar to how seismologists study Earth's interior using earthquakes. These studies have confirmed theoretical models about the Sun's structure and rotation. The Sun's surface rises and falls in complex patterns, an entire star breathing in space. Like music made visible, these ripples reveal hidden harmonies within our star, a cosmic symphony playing in silent wavelengths. Our Sun was born in cosmic fire and turbulence long before our planet existed. It formed approximately 4.6 billion years ago from the gravitational collapse of a region within a large molecular cloud. A passing shockwave, perhaps from a nearby supernova, compressed part of this cloud, initiating the collapse that would become our solar system. As gravity pulled this material inward, conservation of angular momentum caused it to spin faster, while increasing pressure at the center raised the temperature. Eventually, the core became hot enough to initiate hydrogen fusion, and our Sun began to shine. Most of the remaining cloud material formed a disk that would eventually become the planets. The story of our star's birth connects us to the greater galaxy, a tale written in stellar fire that continues to unfold in the slow burning of hydrogen in its heart. The Sun refuses to turn as a single body, spinning instead at different rates from equator to pole. Differential rotation causes the Sun's equator to complete one rotation about 10 days faster than its polar regions. This unusual behavior occurs because the Sun is not solid, but a fluid body of plasma that can flow at different speeds. The effect stretches magnetic field lines that run north and south, twisting them over time like rubber bands. Eventually, these twisted fields become unstable and erupt as solar flares or coronal mass ejections. Earth's atmosphere shields us from the harmful radiation these eruptions produce. Might this strange rotation hold the key to the Sun's cyclical nature? Like a cosmic mixing bowl slowly stirring its contents, our star's uneven turning creates the complex magnetic weather that defines its character. Our Sun grows imperceptibly brighter with each passing eon. Its luminosity has increased by about 30% since it first formed 4.6 billion years ago, and will continue to brighten over billions of years. This gradual brightening occurs as the Sun's core becomes denser and hotter, causing hydrogen fusion to proceed more rapidly. Scientists calculate this change using models of stellar evolution confirmed by observations of similar stars. Early Earth required this dimmer Sun, as its atmosphere contained more greenhouse gases that trapped heat effectively. Without these gases today, Earth would freeze under the same conditions. As our star ages, its gentle brightening continues on a timescale far beyond human perception. Like a candle slowly adjusting its flame, the Sun's increasing brilliance marks the passing epochs of our solar system. Tiny jets of plasma erupt from the Sun's lower atmosphere in countless numbers. Spicules are jet-like eruptions of gas that shoot up from the Sun's chromosphere at speeds of about 20 kilometers per second. These narrow columns of plasma typically reach heights of 10,000 kilometers before falling back or evaporating into the corona. At any given moment, about 300,000 spicules are active on the Sun, creating a brief, ever-changing landscape similar to a field of burning grass. Each spicule lives for only about 5 to 15 minutes before fading away. Scientists believe they form when magnetic reconnection events release energy that propels plasma upward. Like countless flickering candles on the Sun's horizon, these ephemeral jets create a constantly shifting texture on our star's edge, an intricate dance of magnetic forces and superheated gas. Beneath the Sun's visible surface lies a region of constant turbulent mixing. The convection zone extends from about 200,000 kilometers below the surface to the photosphere, where hot plasma rises and cool plasma sinks. This region operates like a pot of boiling water, with material heated at the bottom rising to the surface, where it cools and then sinks again. The convection zone transports energy through physical movement of plasma rather than by radiation. Scientists have mapped this region using helioseismology, which studies sound waves traveling through the Sun. This churning layer creates the granulation pattern visible on the Sun's surface and generates complex magnetic fields. The eternal circulation continues without pause, an invisible engine powering our star's outer layers, bringing energy from the depths to the surface in a cosmic cycle of rising and falling fire. The Sun maintains a remarkable constancy in its energy output despite its dynamic nature. Solar irradiance varies by only about 0.1% during the 11-year solar cycle, demonstrating the Sun's remarkable stability. This slight variation, measured by satellites above Earth's atmosphere, correlates with sunspot activity. Years with more sunspots counterintuitively produce slightly higher total irradiance, as the bright areas surrounding sunspots more than compensate for the darker sunspot regions. This stability has provided Earth with consistent conditions conducive to life for billions of years. Were the Sun more variable, like many other stars, Earth's climate might be too unstable for complex life to evolve. Like a perfectly tuned instrument that never wavers in its note, our star provides the steady energy that makes our biosphere possible. Light born in the Sun's core takes an astonishingly long and meandering path to freedom. The Sun's radiative zone, between the core and convection zone, takes photons tens of thousands of years to traverse due to constant absorption and re-emission. A photon created by fusion in the core will travel only a tiny distance before being absorbed by an atom, which later re-emits it in a random direction. This random walk process means that light zigzags through the dense interior rather than traveling in a straight line. Scientists estimate this journey may take between 17,000 and 150,000 years, though the exact time remains uncertain. The sunlight warming your skin began its journey when humans were still in the Stone Age. In this slow migration of light, we see time itself stretched across space, ancient energy finally released into the cosmos after an epic journey through matter. The Sun has regions where its outer atmosphere seems to vanish into space. Coronal holes are areas of the Sun's corona with lower temperature and density, appearing as dark areas in X-ray and ultraviolet images. These regions form where the Sun's magnetic field lines stretch out into space rather than looping back to the surface. With magnetic lines pointing outward, plasma can escape more easily, creating a constant stream of fast solar wind. Coronal holes are more common during solar minimum and can persist for several solar rotations. When positioned so that Earth falls in their path, they can trigger geomagnetic storms. Might these cosmic windows offer clues to understanding stellar winds throughout our galaxy? Like openings in a cosmic veil, these darker regions allow the Sun's essence to stream more freely into the void, connecting our star directly with interplanetary space. The Sun's energy comes from a delicate dance of subatomic particles in its core. It produces its energy through the proton-proton chain reaction, where 4 hydrogen nuclei combine to form one helium nucleus. This process occurs in 3 stages, with intermediate products of deuterium and helium-3 before creating stable helium-4. Each complete reaction releases 26.7 MeV of energy, primarily as gamma rays and neutrinos. The chance of any single proton fusing is extraordinarily low, but the Sun contains so many protons that fusion happens constantly. This process will continue steadily for another 5 billion years before the Sun's hydrogen fuel begins to deplete significantly. The silent fusion persists without fanfare, atoms merging in microscopic transformations that, multiplied by astronomical numbers, light up our entire solar system. In mere moments, the Sun can accelerate matter to nearly cosmic speed limits. Solar flares can accelerate particles to nearly the speed of light, creating radiation that reaches Earth in minutes. These massive energy releases occur when magnetic field lines suddenly reconnect, converting magnetic energy into kinetic energy and heat. The largest flares can release energy equivalent to billions of hydrogen bombs in just minutes. The high-energy particles they produce can damage satellites, pose radiation risks to astronauts, and create radio blackouts on Earth. Scientists classify solar flares by their X-ray output, with X-class being the most powerful. Through this violent acceleration, the Sun reminds us of its capacity for sudden change. Like cosmic lightning, these brilliant eruptions transform the Sun's stored energy into motion approaching nature's ultimate speed limit. The Sun's invisible force field extends throughout the solar system, shaping cosmic space. The Sun's magnetic field strength at its surface is typically about twice as strong as Earth's magnetic field, though it varies greatly across different regions. This seemingly modest field becomes complex as it is stretched and twisted by the Sun's rotation and plasma flows. The field extends far beyond Pluto, creating a protective bubble called the heliosphere that shields the solar system from galactic cosmic rays. Unlike Earth's relatively stable field, the Sun's magnetic field completely reverses polarity approximately every 11 years. Measurements of the Sun's magnetism help scientists predict solar storms that might affect Earth. This unseen influence shapes our cosmic environment, an invisible architecture extending from our star, defining the very space in which our planet travels. The Sun experiences its own version of earthquakes, rippling across its incandescent surface. Sunquakes are seismic waves triggered by solar flares that ripple across the Sun's surface like earthquakes on a star. These massive wave patterns can span tens of thousands of kilometers and continue for hours after the initial flare. First discovered in 1998, sunquakes produce acoustic waves that penetrate deep into the Sun's interior before bouncing back to the surface. The energy involved in large sunquakes would register as magnitude 11 earthquakes on Earth, thousands of times more powerful than anything in recorded human history. What forces could possibly disturb an entire star? Like ripples in a pond of fire, these stellar tremors reveal the incredible energy contained in magnetic reconnection events, powerful enough to make an entire star ring like a bell. Our planet orbits in a narrow band where liquid water, and therefore life, can exist. The Sun's habitable zone, where liquid water could exist on planetary surfaces, extends from about 0.95 to 1.37 astronomical units from the center of our star. This relatively thin region represents the delicate balance between receiving enough solar energy to prevent water from freezing, but not so much that it all evaporates. Earth orbits at an average distance of 1 astronomical unit, placing it comfortably within this life-supporting region. As the Sun brightens over billions of years, the habitable zone gradually moves outward. Venus once may have been habitable before greenhouse effects made it too hot. Mars, at the outer edge, may have once hosted liquid water. Within this cosmic Goldilocks zone, not too hot and not too cold, our planet found its perfect place. The Sun paints curtains of light in our polar skies through an invisible connection. Solar particles trapped in Earth's magnetic field create the beautiful aurora displays near the polar regions. These charged particles, primarily electrons and protons, spiral along Earth's magnetic field lines toward the poles. When they collide with atmospheric gases like oxygen and nitrogen, they transfer energy that is released as the colorful lights we call auroras. Green auroras come from oxygen at lower altitudes, while red ones originate from oxygen higher up, and blue or purple from nitrogen. The interaction between solar wind and our planet's magnetic shield creates these ethereal displays. Like cosmic messengers carrying whispers from our star, these particles travel across the void to create luminous art in our atmosphere, a visible reminder of Earth's constant dialogue with the Sun. At the center of our star, matter is squeezed beyond earthly comprehension. The Sun's core density reaches about 150 times that of water, compressed by the immense gravitational weight of all that lies above it. This extreme density creates the perfect crucible for nuclear fusion, where atomic nuclei can overcome their natural repulsion to merge and create energy. In this central furnace, a teaspoon of solar core material would weigh as much as a small car on Earth. We exist because matter can be pressed so tightly, atoms nestled against atoms in a dance of pressure and heat. The heart of our star bears the weight of its own existence, creating in its compressed center the light that streams outward to touch distant worlds. Electrons spiral through magnetic fields, singing radio songs to distant listeners. Synchrotron radiation from energetic electrons spiraling in the Sun's magnetic field contributes to radio emissions we can detect on Earth. These charged particles, trapped in invisible magnetic corridors, emit electromagnetic waves as they corkscrew along field lines. Radio astronomers capture these signals, translating them into knowledge about solar storms and magnetic structures we cannot directly observe. What cosmic symphonies might other stars be playing beyond our ability to hear? In the quiet static between radio stations lies the whispered music of our star, electrons dancing along magnetic strings, their curved paths creating melodies that have played continuously since before human ears evolved to listen. To escape the Sun requires a velocity that few objects in our solar system could ever achieve. The Sun's surface gravity creates an escape velocity of about 617 kilometers per second, much higher than Earth's modest 11 kilometers per second. This invisible threshold represents the exact speed needed to break free from the gravitational embrace of our star. The tremendous gravity that creates this barrier is why the Sun holds onto its atmosphere despite its searing heat. Only the fastest particles in the solar wind, accelerated by magnetic processes, can achieve this freedom. The Sun holds itself together through this gravitational boundary, a cosmic doorway that opens only for the swiftest travelers, allowing our star to shine steadily instead of dissipating into space. The Sun's face occasionally grows quieter, with subtle consequences for our blue planet. Solar minimum periods show reduced sunspot activity and can correlate with slightly cooler global temperatures on Earth. During these cyclical lulls in solar activity, fewer sunspots mark the Sun's surface, and its radiation decreases by a fraction of a percent. Historical records of these minimums, like the Maunder minimum between 1645 and 1715, coincided with unusually cold periods in Europe. Scientists continue studying these relationships, seeking patterns in the complex dialogue between star and planet. Like a campfire that occasionally dims, our Sun's rhythmic quieting reminds us of the delicate, energetic balance that cradles life on Earth. A whispered solar secret written in ice cores and tree rings. Light within the Sun becomes lost in a labyrinth of atomic encounters. The Sun's photons are created in the core but take a random walk through the radiative zone, bouncing around for millennia before reaching the surface. Each newly born photon travels only a microscopic distance before being absorbed by an atom and re-emitted in a random direction. This zigzagging journey transforms what could be an 8-minute trip into a migration lasting up to 170,000 years. The sunlight warming your skin began its journey during the last ice age when humans were painting cave walls. Perhaps patience is the most fundamental property of light. To wander for countless lifetimes through darkness before finally emerging as the daylight we so casually take for granted. Ghostly tendrils of magnetized plasma stretch outward from our star like luminous fingers reaching into the void. Coronal streamers are large-scale magnetic structures in the Sun's corona that can extend millions of kilometers into space. Visible during total solar eclipses as pearly rays spreading outward from the darkened disk, these structures trace the Sun's magnetic field as it stretches into the solar system. The streamers form at the boundaries between regions of opposite magnetic polarity, creating arched pathways for plasma to flow outward. They shape the solar wind and influence space weather throughout our planetary neighborhood. In these vast extensions of solar atmosphere, we glimpse how a star reaches beyond itself, its essence flowing outward along invisible magnetic highways that connect our Sun to the most distant planets. Our star is composed of the universe's simplest elements, a testament to cosmic simplicity. The Sun's composition is approximately 73% hydrogen, 25% helium, and 2% heavier elements by mass. This elemental recipe was established when our solar system formed from a collapsing cloud of interstellar gas 4.6 billion years ago. The hydrogen fuels the Sun's nuclear furnace, while the helium is both original material and the product of fusion. The heavier elements, carbon, oxygen, iron, and others were created in previous generations of stars that exploded long ago. We are made from the same cosmic ingredients as our star, just arranged differently. In the Sun's elemental simplicity lies the profound truth that complexity emerges from the most basic components, like cosmic poetry written with a two-letter alphabet. Between Earth and Sun flows an invisible river of energetic particles that can endanger those who venture beyond our atmosphere. Solar energetic particle events can deliver radiation doses equivalent to several chest X-rays to astronauts in space. These storms of accelerated protons and electrons, released during solar flares and coronal mass ejections, race through space at significant fractions of light speed. Earth's magnetic field shields us on the surface, but spacecraft and space travelers must weather these invisible storms. Each eruption creates a wave of particles washing through our solar system, a reminder of the Sun's power. In the quiet void between worlds, these solar messengers carry both creative energy and potential harm. The duality of our star's nature extending far beyond its visible surface. The ocean's rhythmic breathing comes partly from our seemingly distant star. The Sun's tidal forces on Earth are about 46% as strong as the Moon's, contributing to the daily rise and fall of ocean tides. Though less visible than the Moon's influence, the Sun's gravitational pull stretches Earth's oceans into an elongated shape. When Sun and Moon align during new and full moons, their combined tidal forces create the higher spring tides. This celestial partnership has shaped coastlines for billions of years. The rhythm of tides influences countless marine creatures, from crabs to coral. In each wave that washes upon a beach, there exists not just lunar influence, but solar gravity as well. A three-body dance of Earth, Moon, and Sun expressed in the ocean's eternal breathing. In an instant, our star can release more energy than humanity has ever produced. Magnetic reconnection events on the Sun can release energy equivalent to trillions of megatons of TNT in just a few minutes. These events occur when magnetic field lines, stretched and twisted by the Sun's complex motions, suddenly snap and reconfigure like cosmic rubber bands. The potential energy stored in the magnetic field converts explosively into heat, light, and kinetic energy. Though happening 93 million miles away, these eruptions can disrupt radio communications and power grids on Earth. What might we learn if we could harness such power? The Sun reminds us that the universe operates on scales of energy we can barely comprehend, storing and releasing power with both mathematical precision and chaotic beauty. The Sun creates its own magnetic personality through a cosmic dynamo hidden beneath its surface. The Sun's convective motions create a complex magnetic dynamo that generates and maintains its magnetic field. Rising and falling plasma, combined with the Sun's differential rotation, stretches and twists magnetic field lines in a self-sustaining cycle. Like Earth's magnetic field, but vastly more complex, the Sun's magnetism emerges from flowing electrically conductive material, a natural generator powered by heat and rotation. This magnetic personality shapes the Sun's visible features, from sunspots to prominences, and drives the solar cycle. The Sun weaves an invisible tapestry of magnetic force, constantly creating and recreating patterns that extend throughout the solar system, a field of influence that touches every planet with its unseen fingers. Light and heat diminish as they travel outward from our star, following cosmic laws of dilution. Solar irradiance follows an inverse square law, meaning Mars receives only about 43% of the solar energy per unit area that Earth receives. This mathematical relationship governs how energy spreads through space. As the distance doubles, the intensity drops to 1/4. This spreading of sunlight shapes the temperature gradient of our solar system. The law explains why Mercury burns while Neptune remains frozen, despite bathing in the same sunlight. The universe has written this rule into the fabric of space itself. In this elegant spreading of solar energy lies the reason for each planet's character, a single mathematical principle creating both scalding deserts and icy wastes as distance from our star increases. Our Sun bears a cosmic name tag that places it precisely within the stellar family portrait. The Sun's spectral classification as a G2V star indicates its surface temperature, luminosity class, and position on the main sequence. The G2 tells astronomers its surface burns at about 5,178 Kelvin, giving it its yellow-white color. The V designates it as a main sequence star in its prime, steadily converting hydrogen to helium. This stellar classification system, created by studying the light signatures of thousands of stars, helps astronomers understand our Sun in context. Our star is neither exceptional nor unusual, a middle-aged, medium-sized, yellow-white star among billions like it. Perhaps this cosmic ordinariness is what makes it perfect for nurturing life, a stellar parent neither too temperamental nor too dim. Bright islands float upon the Sun's chromosphere, their luminosity revealing hidden magnetic strength. Plagued regions are bright areas in the Sun's chromosphere associated with magnetic field concentrations. Visible in hydrogen alpha light, these glowing patches often surround sunspots, appearing as bright regions against the darker chromospheric background. They form where magnetic field lines cluster together, creating regions of enhanced emission. Plague areas can persist for days or weeks, outlasting the sunspots they accompany. These luminous archipelagos influence Earth's climate by slightly increasing the Sun's energy output during active periods. The magnetic atlas of the Sun is written in light and darkness across its atmosphere, a geography constantly shifting and evolving as the solar dynamo churns beneath, creating islands of brightness that drift across our star's face. Within the Sun, matter itself becomes the fuel for cosmic radiance. The Sun's nuclear fusion converts about 4.3 million tons of matter into energy every second through Einstein's E=mc2 equation. This mass, seemingly lost, transforms directly into the light and heat that sustains our planetary existence. The equation tells us that even a tiny amount of matter contains enormous potential energy. Energy that becomes kinetic only when hydrogen atoms merge to form helium. The Sun has performed this alchemical transformation without pause for billions of years and will continue for billions more. The light touching your skin was once matter in the Sun's core, mass transformed into energy, a conversion that bridges the gap between substance and illumination through the elegance of physical law. The Sun's surface ripples with giant convection cells, creating patterns visible only to the most careful observers. Solar supergranulation patterns create convection cells about 30,000 kilometers across that last for about a day. These enormous cells, large enough to engulf Earth twice over, transport heat and material across the solar surface through rising hot plasma and sinking cooler plasma. Discovered in the 1950s, these patterns move more slowly than the smaller granules that pepper the Sun's surface. The borders between supergranules concentrate magnetic fields, creating networks visible in certain wavelengths. The Sun's face is never truly still, but constantly shifting in a turbulent ballet of rising and falling material. Nature's largest convection pattern, a slow-motion boiling that has continued without pause since our star's formation. Our Sun contains more cosmic spice than most stars in our galactic neighborhood. The Sun's metallicity, or abundance of elements heavier than hydrogen and helium, is about twice that of the galactic average. These metals, which astronomers consider to be all elements except hydrogen and helium, make up only about 2% of the Sun's mass, but play crucial roles in its behavior and evolution. The Sun's relatively high metallicity suggests it formed from material enriched by previous generations of stars that lived and died before our solar system existed. This cosmic inheritance influences everything from the Sun's opacity to its lifetime. Our star carries within it the elemental legacy of countless stellar ancestors, a metallicity that may have made possible the complex chemistry needed for life on the planets that orbit it. Great bridges of plasma arc above the Sun, following invisible magnetic pathways that shape superheated matter. Coronal loops are magnetic flux tubes filled with hot plasma that can arch hundreds of thousands of kilometers above the surface. These luminous structures, visible in extreme ultraviolet and X-ray images, trace the Sun's magnetic field as it emerges from and returns to the solar surface. The plasma flowing along these loops reaches temperatures of millions of degrees, far hotter than the surface below. Some loops remain stable for days or weeks, while others evolve rapidly during solar flares. In these magnificent arches, we see matter itself becoming subservient to magnetism, forced to follow curving roads of invisible force, a demonstration of how energy and field can shape substance into elegant structures that dwarf our entire planet. Our Sun rings like an enormous bell, its entire body vibrating with sound waves that reveal its hidden depths. The Sun's acoustic oscillations have periods ranging from about 3 to 20 minutes creating a constantly ringing star. Millions of different sound waves travel through the Sun simultaneously, each penetrating to different depths before being refracted back to the surface. These vibrations cause the Sun's surface to rise and fall by just a few kilometers, a tiny fraction of the Sun's radius, but detectable with sensitive instruments. Helioseismologists study these oscillations to map the Sun's interior, much as geologists use earthquakes to study Earth's interior. In the Sun's constant singing, scientists have found a window into otherwise invisible stellar depths, cosmic music that carries information about our star's innermost secrets. The solar wind ebbs and flows with the Sun's rhythmic cycle of activity, creating a variable cosmic weather system. Solar wind speed varies with solar activity, ranging from 300 kilometers per second during quiet periods to over 800 during active periods. This stream of charged particles flows outward in all directions, creating a bubble of solar influence called the heliosphere that extends far beyond Pluto. The fast wind originates from coronal holes near the solar poles, while the slower wind comes from regions near the solar equator. This interplanetary breeze pushes against the interstellar medium, creating a boundary where our star's influence fades. The breathing of our star, its cyclical exhalation of particles, creates a living system of energy and matter that envelops all planets, a sphere of solar essence expanding into the void. The Sun appears to fade toward its edges, a subtle gradient that reveals atmospheric secrets. The Sun's limb-darkening effect makes its edges appear dimmer than the center when viewed through proper solar filters. This gradient occurs because we see different depths into the Sun at different angles. At the center, we peer deeper into hotter, brighter layers, while at the edges, our line of sight passes through cooler, more absorbing outer layers. This effect helps astronomers measure the Sun's temperature structure and how opacity changes with depth. The same phenomenon occurs on other stars, but is only directly observable on our Sun. The gentle fading from center to edge reminds us that even apparent brightness contains hidden information about depth and structure, a lesson in how perspective reveals layered truth. A constantly shifting mosaic of tiny magnetic loops creates a dynamic carpet across the solar surface. Magnetic carpet patterns on the Sun's surface consist of small-scale magnetic field loops that constantly emerge and submerge. These minor magnetic features, typically spanning a few thousand kilometers, have lifetimes of only hours or days before dissipating. Thousands of these loops pepper the Sun at any moment, creating a constantly renewing magnetic landscape. Though individually small, their collective energy release may help explain the mysterious heating of the Sun's corona. The Sun's surface is never magnetically quiet, but rather hosts a continuous emergence and dissolution of field structures. This magnetic tapestry represents the smallest scale of solar activity, a background hum of magnetic emergence and reconnection that never ceases, even during the quietest solar periods. Our star spins differently than the planets it governs, distributing its momentum in a pattern unique to fluid celestial bodies. The Sun's angular momentum is distributed differently than planets, with most of it contained in the outer convective layers. Unlike solid bodies like Earth, where mass closer to the center rotates faster, the Sun's equator rotates more quickly than its poles. This differential rotation stretches magnetic field lines and drives the solar dynamo. The Sun rotates once at its equator in about 25 days, but the core may rotate on a different schedule entirely, a mystery still being unravelled. In this peculiar distribution of motion lies the engine of solar activity, the reason our star doesn't shine with perfect constancy. The Sun's spiral dancing creates the magnetic personality that makes it not just a light source, but a dynamic, evolving system. The Sun announces its most violent eruptions with invisible radio broadcasts that race ahead of physical matter. Solar Type II radio bursts are produced by shock waves from coronal mass ejections traveling through the corona. These distinctive radio signals, first detected in the 1950s, sweep from high to low frequencies as the shock wave moves outward through less dense plasma. Radio astronomers use these emissions as early warning systems for solar storms that might impact Earth. The radio signature travels at light speed, arriving well before the physical particles that might disrupt satellites or power grids. In these ethereal radio whispers, the Sun telegraphs its activities across space, a cosmic herald announcing the approach of solar storms, providing precious hours of warning before the physical impact reaches Earth's magnetic field. The Sun's precise surface temperature determines the very color of light that illuminates our world. The Sun's effective temperature of 5,778 Kelvin determines its peak emission wavelength in the visible light spectrum. This temperature creates a spectrum that peaks in the green-yellow portion of visible light, though our eyes perceive the combined spectrum as white or yellow-white. This specific temperature results from the balance between gravitational compression and outward pressure from nuclear fusion. The evolution of Earth's life, including human vision, has been shaped by this particular stellar temperature and its resulting spectrum. Had our star been slightly hotter or cooler, the quality of light reaching Earth would differ, potentially altering the entire course of biological evolution. Our very perception of color emerges from our star's thermal character. Sometimes, the Sun's activity briefly shields us from the constant rain of cosmic rays from deep space. Forebush decreases occur when solar wind changes temporarily reduce the cosmic ray flux reaching Earth's atmosphere. During these events, typically following coronal mass ejections, the enhanced solar magnetic fields sweep through the inner solar system, deflecting the galactic cosmic rays that constantly bombard Earth. These decreases, first identified by physicist Scott Forbush in the 1930s, typically last a few days before cosmic ray levels gradually return to normal. They demonstrate how the Sun's activity modulates our exposure to galactic radiation. In these temporary cosmic ray shadows, we glimpse how one type of radiation can shield us from another, a complex interplay between our star and the galaxy beyond, an astronomical umbrella briefly unfurled against deeper cosmic weather. The Sun's magnetic field carries a geometric quality that determines its most explosive behavior. The Sun's magnetic helicity, or twist in magnetic field lines, plays a crucial role in coronal mass ejection formation. This mathematical property describes how magnetic field lines wrap around each other, storing energy like a wound spring. When helicity accumulates beyond a critical threshold, the field becomes unstable, potentially triggering an eruption. Conserved during solar plasma movement, helicity transfers from small to large scales as fields merge. Some solar regions show a preference for left or right-handed twist, influenced by the Sun's rotation. The mathematics of magnetic geometry guides the Sun's most dramatic moments, a cosmic choreography where invisible lines twist and tangle until they can no longer hold their form, releasing their stored energy in spectacular eruptions that can reach Earth days later. Scattered throughout our galaxy are stellar twins to our Sun, offering glimpses of our star's past and future. Solar analogues are other stars with similar mass, temperature, and metallicity that help astronomers study stellar evolution. By observing these solar doppelgangers at various ages, scientists can piece together our Sun's biography and destiny. Some analogues may be younger versions of our star, showing how it behaved billions of years ago, while others represent its future states. The most perfect solar twins match our Sun in almost every measurable property, rare cosmic mirrors. Through these stellar siblings, astronomers read the life story of our own star, chapters we could never directly observe in a human lifespan. The Sun's extended family offers a glimpse across time, solar reflections scattered through space like pages from an astronomical autobiography. Our star maintains a perfect balance between opposing cosmic forces, creating stability that nurtures life. The Sun's radiative losses are precisely balanced by nuclear energy production, maintaining hydrostatic equilibrium. Each second, the Sun radiates enormous energy into space, which would cause it to cool and contract if not for the continuous nuclear fusion in its core. This perfect balance between gravity pulling inward and pressure pushing outward has maintained the Sun's size and energy output for billions of years. Should this equilibrium be disturbed, the Sun would expand or contract until a new balance point is reached. The mathematics of this stellar stability allow for planetary orbits that remain consistent enough for life to evolve. In this cosmic equilibrium, we find not chaos, but precision. A star neither expanding nor contracting, but simply being its steady presence, a foundation for life itself. Sometimes the Sun's atmosphere briefly darkens as matter is flung into space. Coronal dimming occurs when coronal mass ejections remove plasma from the corona, creating temporary dark regions. These dimming events, visible in extreme ultraviolet and X-ray observations, represent actual reductions in coronal density as billions of tons of material are expelled into space. The darkened regions can persist for hours or days before the corona refills with plasma. Scientists use these dimmings to track and measure coronal mass ejections, even when they're directed toward Earth and difficult to observe directly. The Sun's atmosphere briefly grows thinner, creating shadows where matter once was, before slowly refilling the void. These cosmic exhalations remind us that even the Sun's seemingly permanent features are in constant flux, its very atmosphere occasionally thinning as it casts material into the void. Sound waves race through the Sun's interior, carrying whispers of its hidden structure to those who know how to listen. The Sun's P-mode oscillations are pressure waves that penetrate to different depths, revealing internal structure through helioseismology. These acoustic waves, caused by turbulence in the convection zone, travel at different speeds and angles through the Sun's interior before returning to the surface. By measuring thousands of these oscillations with space telescopes like SOHO, scientists have mapped the Sun's internal rotation, composition layers, and convective flows. These solar seismic waves travel at around 500,000 kilometers per hour, crossing the entire Sun in about 2 hours. The Sun's interior sings with countless overlapping vibrations, a complex harmonic structure that carries, encoded within its frequencies, the secret architecture of our star's hidden heart. Our sun's rhythmic personality has changed over centuries, its cyclic nature more variable than once thought. Solar activity cycles appear to have varied in length and intensity over the past several centuries based on historical records. The 11-year cycle we know today has not always been so regular. During the Maunder Minimum 1645-1715, sunspots became extremely rare, coinciding with a period of unusual cold in Europe and North America. Other historical minimums and maximums have been identified through analysis of tree rings and ice cores, which record cosmic ray flux influenced by solar activity. Even in our modern understanding, consecutive solar cycles show significant differences in duration and strength. The sun breathes not with the regularity of a metronome, but with the organic variation of a leaving system, its rhythms evolving through centuries. A stellar personality with moods that span human generations. The sun's magnetic field becomes a vast reservoir of potential energy, a cosmic spring wound tight before its release. The sun's magnetic field lines can store enormous amounts of energy in twisted and stressed configurations. Like rubber bands stretched and twisted, these fields contain potential energy that can be suddenly released during solar flares and coronal mass ejections. The energy builds up gradually as the field is distorted by the sun's differential rotation and plasma movements. Scientists estimate that major eruptive events can release energy equivalent to billions of hydrogen bombs in minutes. This invisible storage of power occurs through the entire solar atmosphere, creating regions of accumulated tension. The sun holds its energy in magnetic form before transforming it into light, heat, and motion. Invisible becomes visible as field lines reconfigure, releasing their stored potential in brilliant bursts that illuminate our entire solar system. Swift atomic messengers race from the sun during its most energetic moments, reaching Earth before their charged counterparts. Solar neutrons produced in energetic flares can reach Earth's atmosphere within an hour of the initial event. But unlike charged particles that follow curved paths along magnetic field lines, neutrons travel in straight lines at nearly the speed of light. Their brief lifetime of about 15 minutes means only the fastest neutrons from the most powerful flares survive the journey to Earth. Special neutron monitors at high-altitude research stations detect these rare particles, providing unique information about acceleration processes during flares. These fleeting atomic travelers, born in solar violence and destined for quick decay, carry untainted information about their birth conditions. They arrive like cosmic messengers. Their brief existence a direct connection between Earth and the most energetic processes on our star's surface. Deep within the sun, rotation becomes a complex layered phenomenon that drives its magnetic heart. The sun's rotation rate decreases with depth in the convection zone, a phenomenon called angular velocity shear. This differential rotation creates boundaries where layers moving at different speeds rub against each other, generating the shear forces crucial for the solar dynamo. At the tachocline, the boundary between the radiative and convective zones, this shear is particularly strong. Helioseismology has mapped these internal rotation patterns, showing how the sun's spin varies not just from equator to pole, but from surface to core. the hidden machinery of solar rotation turns at different rates in different layers, creating the conditions for magnetic field generation. Within these sliding layers of plasma, moving at different speeds, lies the engine of solar activity, an invisible dynamo powered by cosmic friction. Great dark arches mark boundaries of magnetic territory near the Sun's poles. Polar crown filaments are long, dark structures near the Sun's poles that mark the boundaries between magnetic regions. These massive features can stretch across hundreds of thousands of kilometers, appearing as dark snaking lines when viewed in certain wavelengths. They form where magnetic fields of opposite polarity meet, creating channels where cooler, denser plasma can collect above the surface. These filaments migrate poleward throughout the solar cycle, marking the progress of the magnetic cycle. Sometimes they erupt, sending their material into space as part of coronal mass ejections. These dark coronas near the solar poles represent one of the Sun's largest scale features: magnetic boundaries drawn across its face, dividing territories in the complex geography of solar magnetism that constantly shifts throughout its 11-year heartbeat. The deepest oscillations of our Sun remain largely hidden, their existence more theory than observation. The Sun's G-mode oscillations are gravity waves that could provide information about the core rotation rate. Unlike the well-studied pressure waves, P-modes, that dominate the Sun's surface vibrations, gravity waves are extremely difficult to detect because they have very small amplitudes at the surface. These waves are trapped in the Sun's interior, where buoyancy serves as their restoring force. Despite decades of searching, only indirect evidence of G-modes has been found. If clearly detected and measured, they could reveal the rotation rate of the Sun's core and other properties of its deepest regions. The Sun may be singing in bass notes too low for our instruments to clearly hear. A profound cosmic music carrying information from the stellar depths, vibrations that remain one of solar physics' most elusive quarries. Our star's rhythms remain partially unpredictable, a complex system that resists perfect forecasting. Solar cycle prediction remains challenging due to the complex, chaotic nature of the magnetic dynamo process. Despite sophisticated computer models and centuries of observations, scientists still struggle to accurately predict the timing and strength of future solar cycles. The interactions between plasma flows, differential rotation, and magnetic field generation create a system with chaotic elements that amplify small uncertainties. Current predictions typically have significant error margins, especially for long-term forecasts. The Sun maintains some mystery about its future behavior, a reminder that even our closest star isn't fully predictable. In this solar uncertainty lies a lesson about complex systems throughout nature. Their emergent behaviors resist complete reduction to simple formulas, their futures remaining partially veiled despite our deepening understanding of their mechanisms. A vast river of plasma flows in a stately circuit from the Sun's equator to its poles and back again. The Sun's meridional circulation is a slow flow pattern that transports material from equator to poles and back. This massive conveyor belt moves at only a few meters per second, but carries magnetic flux that helps drive the solar cycle. The surface flow moves toward the poles, while a return flow deep within the convection zone completes the circuit. This circulation takes about 11 years to complete one loop, matching the solar cycle length. The pattern helps transport magnetic elements poleward, contributing to the reversal of the Sun's polar fields. The Sun organizes its internal movements not just in rising and falling convection, but in great circulating currents that span from equator to pole, invisible rivers of plasma flowing in patterns that help orchestrate its magnetic heartbeat. Countless tiny explosions pepper our star's surface every moment, their collective energy possibly solving a long-standing solar mystery. Microflares occur constantly across the Sun's surface, releasing energy equivalent to millions of hydrogen bombs. These miniature versions of solar flares, too small to be seen without specialized instruments, happen thousands of times daily across the Sun. Some scientists believe their cumulative energy might help explain the coronal heating problem, why the Sun's atmosphere is hundreds of times hotter than its surface. Each microflare releases a small amount of energy as magnetic field lines reconnect at small scales. The Sun whispers its power not just in grand eruptions, but in millions of tiny energy releases, a background crackle of activity that never ceases. In these smallest expressions of solar energy, we may find the answer to one of our star's most persistent mysteries: its atmospheric temperature, written in microscopic magnetic text. In the flowing plasma of our Sun, magnetic fields move with graceful persistence. The Sun's magnetic Reynolds number is extremely high, indicating that magnetic diffusion is much slower than convective motions. This means the magnetic field lines are essentially frozen into the plasma, moving wherever the solar material flows. You can see this connection in the arched prominences that follow magnetic pathways, linking you to forces that shape our entire solar system. When you watch a sunrise, you're witnessing light filtered through a magnetic landscape that has traveled intact from deep within our star. The threads that connect us to our Sun are not just light and warmth, but invisible magnetic structures carried on solar winds that eventually caress our own planet's magnetic field. A cosmic embrace billions of years in the making. Between your fingertips and the Sun lies a sea of changing balance between invisible forces. Solar plasma beta, the ratio of gas pressure to magnetic pressure, varies dramatically from core to corona. Near the surface, gas pressure dominates, while in the outer atmosphere, magnetic forces take control. This shifting balance determines how energy moves through our star and eventually reaches us. We experience this same dance of pressures in our own lives, moments when we need to yield and flow, and others when we must hold our shape against surrounding currents. Your morning sunlight carries the signature of this delicate equilibrium, a reminder that even the mightiest forces in nature must find their balance. In these invisible harmonies, our Sun teaches us that strength and flexibility can coexist in the same moment. The great rivers of plasma that stir our Sun move with a rhythm older than humanity. The Sun's convective turnover time is approximately 1 month for the largest convection cells. These massive movements, carrying heat from below to the surface, operate on a timescale we can intuitively understand. While your heart beats once a second and you breathe every few seconds, the Sun's great circulation completes one cycle as the Moon orbits Earth. We are connected to our star not just through light and energy, but through shared patterns of circulation. Your blood, Earth's oceans, and the Sun's plasma all flowing in life-giving cycles. When you feel the warmth of sunlight, you're touching the result of movements that began their journey upward when the Moon was in a different phase. tiny islands of brightness dot the sun's atmosphere, marking places where your star remembers. Coronal bright points are small, long-lived features associated with magnetic bipoles that can persist for hours or days. These luminous anchors scattered across the corona shine like memories held in place by magnetic connection. Just as certain thoughts remain with you through the day, these bright points maintain their presence amid the constant flow of solar plasma. They remind us that even in spaces of incredible energy and movement, points of stability can form and endure. When you look up at the sun, safely through proper filters, know that within its shimmering corona are bright moments of continuity, small beacons of light that, like cherished memories in your own life, persist through time. The sun's embrace grows, gentler with distance, its magnetic touch fading into the void. The sun's magnetic field strength decreases exponentially with height in the quiet corona. This gradual weakening creates a natural transition from the ordered structure near the surface to the freedom of open space. We experience similar diminishing influences in our lives. The voice of a loved one fading as they walk away, or childhood lessons that soften but never quite disappear. You exist in the extended magnetic field of our sun, where its influence has diminished enough to allow Earth's own magnetic personality to flourish. In this perfect balance point, not too strong, not too weak, life finds its place, cradled in the fading whisper of solar magnetism that still shields us from the deeper cosmos. The breath of our sun begins close to its surface, gathering speed as it journeys outward. Solar wind acceleration occurs primarily within the first few solar radii above the surface through wave heating mechanisms. This invisible exhalation, which eventually bathes our planet, finds most of its momentum near its source. Like words that gain power in the moment they're spoken, or intentions that find their strength when first formed, the solar wind discovers its velocity at the beginning of its journey. You feel the distant result of this acceleration when auroras dance in polar skies, a connection between your world and the sun's extended atmosphere. When you watch these celestial lights, remember they begin with a push close to the solar surface, a gentle origin for a cosmic breath that eventually embraces our entire planet. On our sun's shining face, invisible patterns write stories both intimate and vast. The sun's photospheric magnetic field has a complex structure with both small-scale and large-scale components. This multi-layered tapestry combines fleeting magnetic fragments with grand patterns that span the entire solar surface. You experience similar complexity in your own life. Small daily moments woven into the larger patterns of your years. The sun's magnetic landscape ranges from tiny ephemeral regions to massive structures that persist for months, each scale affecting the others in continuous dialogue. When sunlight warms your skin, you're touching the visible manifestation of this invisible architecture. Through this magnetic connection, we're reminded that complexity can create beauty and that patterns can exist at every scale of observation. Like the seasons of Earth, our sun breathes in cycles of magnetic abundance. Magnetic flux emergence rates on the sun vary with the solar cycle, peaking during solar maximum periods. This rhythmic blossoming of magnetism follows an 11-year heartbeat, a tempo that has continued for thousands of years before your birth. Your life unfolds within these greater cycles, whether you notice them or not. When the sun reaches its magnetic peak, more auroras dance in our skies and more sunspots dapple its surface. We share this tendency toward cycles, times of activity and rest, creation and reflection. The next time you witness a particularly vibrant sunset, consider that you might be seeing light filtered through a sun at the height of its magnetic expression, a moment of solar abundance illuminating your world. Some questions about our sun remain beautifully unanswered, inviting our continued wonder. The sun's coronal heating problem remains one of the major unsolved puzzles in solar physics. The mystery lies in why the sun's atmosphere reaches temperatures hundreds of times hotter than its surface, like finding the air above a campfire hotter than the flames. You share this journey of questioning with generations of scientists who have pondered this paradox. There's comfort in knowing that even our most familiar star, the one we've observed longer than any other, still holds secrets. When you feel the sun's warmth on your face, you're connecting with both what we understand and what we don't. In these unresolved questions lies the beautiful truth that the universe remains open to exploration, waiting for curious minds to continue the search. The sun sometimes calls its children home in graceful arcs of return. Solar energetic particles can spiral along magnetic field lines, sometimes returning to impact the sun's surface. These high-speed travelers, accelerated during solar eruptions, don't always escape into space, but can be guided back by the same magnetic forces that launched them. We recognize this pattern of departure and return in our own lives. Thoughts sent out that come back transformed, or journeys that eventually lead us home. You exist in a similar embrace of forces seen and unseen, guided by influences that both launch you forward and sometimes bring you back to your beginnings. When you watch the sun set, imagine these invisible pathways of return, cosmic loops that remind us that even in the vastness of space, connections remain and circles complete. Your sun rotates with different voices, singing a complex harmony of motion. The sun's differential rotation profile has been precisely measured using helioseismic techniques that listen to sound waves traveling through the solar interior. This layered turning, with the equator completing a rotation in 25 days while the poles take 35, creates the very magnetic personality of our star. You feel the results of this uneven rotation in the solar cycle that subtly influences Earth's climate and space environment. Like the various rhythms in your own life, heartbeat, breathing, sleeping, waking, the sun maintains multiple timekeeper. When you watch a sunrise, you're witnessing light from a star whose complex internal rhythms have remained steady for billions of years, a cosmic constancy that has nurtured life on Earth through countless generations of your ancestors. Great solar storms race through space at speeds that stagger imagination. Coronal mass ejection speeds can range from 50 to over 3,000 kilometers per second, depending on their driving mechanism. These massive eruptions of plasma and magnetic field can travel from the sun to Earth in as little as 15 hours, or as long as several days. You exist in the path of these ancient solar breaths, protected by Earth's magnetic field, yet still connected to their ebb and flow. The northern lights that inspire wonder are often the visible signature of these solar storms embracing our world. When you look up at a clear night sky, remember that space between you and the stars isn't empty but alive with these solar exhalations, carrying messages from our star across the void. a constant conversation between sun and earth that has continued since before the first humans looked skyward. The sun's magnetic landscape shifts through both gentle diffusion and flowing rivers of plasma. The sun's magnetic flux transport involves both diffusion and advection by large-scale flows that carry magnetic elements across the solar surface. This dual movement creates the ever-changing magnetic face of our star. You witness similar processes in your own thoughts, some ideas spreading slowly outward, while others are carried along streams of attention. The magnetic patterns that eventually shape space weather around Earth begin with these solar transport mechanisms, connecting your daily life to processes occurring 93 million miles away. When satellites transmit your messages or solar panels power your home, you're benefiting from our understanding of these magnetic journeys. In the dance between diffusion and flow, the sun finds balance between change and continuity, a harmony we seek in our own lives. The story of our sun stretches far beyond human memory, written in tree rings and ancient ice. Solar irradiance reconstruction from proxy data suggests variability on centennial and millennial timescales, revealing solar patterns that have influenced Earth's climate for thousands of years. You walk in the light of a star whose subtle shifts in brightness have helped shape the world you know. When you touch the rings of an ancient tree, or consider ice cores drawn from glaciers, you're connecting with records of the sun's changing moods long before written history. The sunlight falling on your skin today carries forward a pattern that extends backward through time immemorial. In this continuity between past and present, between solar variations and Earth's response, we find ourselves part of a story much larger than any single human life. A delicate network of brightness traces the boundaries of giant convection cells on the sun. The sun's chromospheric network outlines supergranulation cells and marks regions of enhanced magnetic field where plasma flows converge. This luminous webwork, visible in certain wavelengths of light, reveals the underlying structure of solar convection. You carry similar networks of connection in your own body. The branching patterns of veins, nerves, and lymphatic vessels that follow the contours of your physical form. When morning light filters through your window, you're welcoming energy that was born in nuclear fusion, rose through convection, and traveled along this chromospheric network before beginning its journey to Earth. The patterns that organize matter and energy on our star mirror. The patterns that organize life itself. A shared geometry connecting your existence to cosmic processes. In quiet meetings across the sun's surface, opposing magnetic forces find reconciliation. Magnetic flux cancellation occurs when opposite polarity field lines meet and reconnect at the photosphere, a process that converts magnetic energy into heat and motion. These small magnetic annihilations happen constantly across the solar surface, part of the sun's continuous magnetic evolution. You might recognize similar patterns in your own experience. How tensions resolve, opposites sometimes neutralize each other, and energy changes from one form to another. The sunlight warming your garden carries the signature of these magnetic reconciliations, energy transformed and released through the meeting of opposing forces. When you feel the gentle touch of sunlight, remember it emerges from both creation and cancellation, a balance of processes that, like the cycles of your own life, include both building up and letting go. Our star's atmosphere allows us to see through it, revealing layers that would otherwise remain hidden. The sun's corona is optically thin at most wavelengths, allowing us to observe its three-dimensional structure as layers of light and energy stack upon each other. This transparency gives us unprecedented views into the architecture of our star. You share this quality in moments of openness, when what lies within becomes visible to those around you. The solar eclipse that reveals the corona's ghostly glow reminds us that sometimes seeing clearly requires the right conditions and perspective. When you look at telescope images of the Sun's outer atmosphere, you're witnessing light that has traveled through multiple layers of solar material, each adding its signature to the journey. In this celestial transparency, we find both scientific understanding and a metaphor for clarity in our own lives. When solar winds meet planets, they create invisible sculptures of current and light. Solar wind interaction with planetary magnetospheres creates complex current systems and particle acceleration regions that shape the space environment around worlds like our own. These interactions form magnetospheric cavities that protect planetary atmospheres while creating phenomena like auroras. You live within Earth's magnetosphere, a protective bubble carved by the Sun's outflow. The solar particles that sometimes make their way along magnetic field lines to create northern lights connect you directly to solar processes. When you witness an aurora's shifting curtain, you're seeing the visible manifestation of this planetary shield responding to the Sun's touch. In these luminous boundaries between stellar influence and planetary protection, we find evidence of a relationship that has helped make Earth habitable for billions of years. The Sun's magnetic personality follows consistent patterns across cosmic time. The Sun's magnetic field polarity follows Hale's law, with consistent patterns that reverse every solar cycle according to specific rules of orientation. This magnetic choreography has continued for countless cycles before humans first noticed it. You experience the results of this magnetic discipline in the reliable solar cycle that subtly influences Earth's climate and space environment. Like the changing seasons that you trust will return, the Sun's magnetic reversals follow dependable patterns that have provided stability for life on Earth. When you plant a garden in spring sunshine, you're participating in rhythms connected to both Earth's tilted journey and the Sun's magnetic cycles. In these interlocking patterns, from magnetic polarity to seasonal growth, we find the reliable foundations that support all living things. Patient sentinels float in space, keeping constant watch over our life-giving star. Solar observation satellites positioned at the L1 Lagrange point provide continuous monitoring of solar activity from a location 930,000 miles from Earth. These technological guardians, balanced between competing gravitational pulls, give us warning of solar storms that might affect our world. You benefit daily from this vigilance through protected power grids and communication systems. Like ancestral watchers who once tracked seasonal changes to prepare their communities, these space-based observers extend our awareness beyond Earth's boundaries. When you check a weather forecast or use GPS navigation, you're connecting with a system that depends on understanding solar conditions. In this extended cosmic awareness, humanity has created a new relationship with our star, one that combines ancient reverence with modern scientific insight. Ghostly particles from the Sun's heart stream through your body in silent affirmation of our understanding. The Sun's neutrino flux measured on Earth confirms our understanding of nuclear fusion processes in the core. with trillions of these nearly massless particles passing through you each second. These elusive messengers travel directly from the Sun's center to Earth in just 8 minutes, carrying information from a place no light can escape directly. You are transparent to these solar neutrinos, your very being permeable to their passage. When scientific instruments detect these particles, they verify theories about what powers our star. The next time you feel the sun's warmth, remember that beyond the visible light warming your skin, a flood of neutrinos is passing through you, connecting your body directly to the nuclear heart of our solar system. The sun's atmosphere rings like a vast musical instrument, revealing its secrets through vibration. Coronal seismology uses wave observations to infer physical properties of coronal plasma structures, letting scientists measure what cannot be directly touched. These waves, moving through the sun's outer atmosphere, carry information about temperature, density, and magnetic field strength. You experience similar revelations through the vibrations that reach your ears as music or voice, invisible waves that carry meaning across space. When you see time-lapse videos of the sun's corona pulsing with waves, you're witnessing the same physical principles that allow sound to move through air. In these oscillations that reveal what lies beyond direct measurement, we find both scientific insight and a reminder of how much can be understood through careful attention to nature's subtle movements. Our star maintains a cosmic accounting system where every magnetic element must find its balance. The sun's magnetic flux budget must balance over long timescales through flux emergence and cancellation processes, with new magnetic elements rising to the surface while others merge and disappear. This equilibrium maintains the sun's overall magnetic structure through constant change. You might recognize similar patterns in natural cycles around you: water evaporating and returning as rain, or forests growing from what was once released by decay. The sunlight that nurtures life on Earth emerges from this balanced system of magnetic creation and destruction. When you observe a sunset's colors spreading across the sky, you're witnessing light filtered through the results of this perfect magnetic accounting. A reminder that even in constant change, balance can persist across cosmic timescales. Our sun exhales a steady stream of itself into the vastness of space. Solar wind mass flux varies with solar activity, carrying away approximately 1 million tons of material per second into the solar system. This constant outflow, though just a tiny fraction of the sun's enormous mass, has shaped the environment around all planets over billions of years. You live within this extended solar breath, your planet's magnetic field and atmosphere interacting with this stream of particles that left the sun days earlier. The solar wind that triggers auroras and affects satellite operations connects you directly to solar processes occurring millions of miles away. When you look up at the night sky, remember the space between planets is filled with this solar exhalation, an invisible current flowing outward from our star, carrying its influence to the farthest reaches of its gravitational domain. Below the sun's churning surface, a delicate boundary marks where chaos meets order. The sun's convective penetration into the radiative zone affects the internal structure and mixing processes where turbulent convection meets the more stable radiative interior. This transitional region, called the tachocline, plays a crucial role in generating the solar magnetic field. You experience similar boundaries in your own life, places where different aspects of yourself meet and interact, creating something new at the intersection. The energy that warms your world passes through this boundary on its journey outward from the solar core. When you feel sunlight on your face, you're connecting with heat that was once deep in the radiative zone before being carried upward by convection. In these interior transitions, hidden from direct view, our star organizes the processes that ultimately make life on Earth possible. The Sun preserves a mathematical quality as magnetic fields twist and evolve through space. Magnetic helicity conservation plays an important role in solar flare and coronal mass ejection dynamics, maintaining the twistedness of magnetic fields even as they reconfigure during eruptions. This preserved quantity shapes how energy is released during solar storms. You might notice similar conservation principles in other natural systems, how water maintains its volume when changing form, or how momentum transfers between objects. The solar eruptions that sometimes affect Earth's space environment carry this preserved helicity outward into the solar system. When communications or power systems respond to solar storms, they're interacting with magnetic structures whose fundamental twisted nature has been maintained across millions of miles of space, a cosmic continuity between our star and its planetary neighborhood. Our Sun follows a stately path of evolution that will eventually transform its relationship with Earth. The Sun's long-term evolution will see it gradually expand and brighten over the next several billion years, as hydrogen in its core depletes and its internal structure shifts. This slow change, imperceptible in human timescales, has already increased the Sun's brightness by about 30% since Earth's formation. You exist during a perfect moment in this stellar journey, when the Sun's output creates conditions ideal for life as we know it. The warmth you feel today will slowly intensify over eons until Earth's oceans eventually evaporate. When you watch a sunset, you're witnessing a star in middle age halfway through its main sequence life, providing the steady energy that allows you to exist in this cosmic moment. The rhythm of our Sun's heartbeat may be controlled by invisible currents flowing from equator to pole. Solar cycle amplitude variations may be related to the strength of the meridional circulation flow, with stronger flows potentially leading to weaker solar cycles. This relationship connects the Sun's interior motions to the magnetic activity we observe on its surface. You experience the subtle effects of these solar cycles in Earth's climate and space environment, living within the embrace of these stellar rhythms. Like ocean currents that influence weather patterns, these solar flows shape the conditions that ultimately reach our planet when you plant gardens according to the seasons or plan activities around weather forecasts. You're adjusting to conditions influenced by these grand solar circulations. In this connection between internal stellar processes and your daily life, we find evidence of our deep integration with cosmic rhythms. A constantly changing tapestry of magnetism covers the Sun's surface in patterns too small to see from Earth. The Sun's magnetic carpet evolution occurs on timescales of hours, as small flux elements emerge and disappear, creating a dynamic magnetic landscape that completely renews itself every few days. This ever-shifting foundation influences all larger solar structures. You might recognize similar patterns of constant renewal in natural systems around you. The replacement of skin cells, the regeneration of forest undergrowth, or the exchange of air in your lungs. the sunlight warming your world passes through this magnetic tapestry on its journey to Earth. When you bask in sunshine, you're connecting with energy that navigated this intricate magnetic landscape moments before beginning its 8-minute journey to reach you. A connection to processes unfolding on our star even as you read these words. Scientists map invisible fields extending from the Sun to predict cosmic weather that might affect Earth. Coronal magnetic field extrapolation from photospheric measurements helps predict space weather events by modeling how magnetic structures in the Sun's atmosphere might evolve and erupt. These mathematical projections extend what we can measure into what we can't directly observe. You benefit from this extended perception through warnings about solar storms that might affect power grids, satellites, or communication systems. Like ancient navigators who predicted storms by watching clouds on the horizon, modern heliophysicists scan the Sun's magnetic patterns for signs of what might come. When your GPS works reliably, or your lights stay on during solar activity, you're experiencing the practical benefits of humanity's ability to understand and anticipate the Sun's magnetic behavior, an invisible shield of knowledge protecting our technological society. Deep within our star, a remarkable uniformity of motion prevails beneath the chaos above. The Sun's radiative zone rotation rate remains nearly constant with radius, unlike the convective zone above with its differential rotation. This inner region, making up about 70% of the Sun's radius, rotates as if it were a solid body, though it's made of plasma. You might find reflection of this in your own life. Beneath daily variations, perhaps there exists a core self that maintains its nature through time. The energy warming your skin began its journey through this steadily rotating region, carrying the signature of both constancy and change. When you feel the Sun's heat, you're connecting with a star whose inner stability and outer dynamism together create the perfect conditions for life on Earth, a balance between dependable presence and creative variation. The solar wind carries information about its birthplace encoded in the electrical states of its atoms. Solar wind charge state measurements provide diagnostics of coronal electron temperature at the source regions, allowing scientists to determine conditions in the Sun's atmosphere from particles collected near Earth. These ionic signatures remain frozen in during the wind's journey through space. You too carry markers of your origins that remain with you through life's journey. The solar particles that sometimes trigger auroras in our skies bring with them this record of their creation, a message from our star written in atomic structure. When you witness these colorful displays, you're seeing not just the beautiful result of solar-terrestrial interaction, but the visible end of a journey that began in specific regions of the Sun's corona, carrying their temperature signature across interplanetary space to illuminate our night skies. As our golden journey fades like sunset into twilight, the brilliant facts about our Sun begin to dim and soften in your mind. We've basked in the warm glow of solar knowledge, from magnetic fields that dance across its surface, to the mysterious corona that still puzzles scientists, to the solar wind carrying the Sun's essence throughout our system. You are connected to this radiant star in ways both profound and intimate. The light warming your skin traveled across the vacuum of space for 8 minutes to reach you. As you rest here on Earth, you are cradled in the protective embrace of our star's magnetic field, shielding you as you drift towards sleep. Tonight, As your consciousness ebbs like the setting sun, the solar processes continue their ancient rhythms. Magnetic flux emerges and cancels. Convection cells turn over. The sun's quiet work continues while you rest in its distant warmth, a child of stardust returning to dreams. If sleep hasn't quite found you yet, another episode awaits to guide you further into cosmic slumber. May your dreams be as peaceful as the sun's core, and as warm as its nurturing rays. Good night, fellow traveller in our solar journey. Good night.